Hello again everybody, thank you for joining me for another video. Today we're going to prove a compound angle formulae for A-level maths using nothing but GCSE right angled trigonometry and some fairly basic geometry. So let's have a look how this is going to work. Our target of course is to prove the double angle formulae, so we're going to be proving these results as follows. Then using some other identities we're going to also prove these three as well. So there's going to be 6 different ones in total we're going to come to. So, what we're going to do is we're going to make a special rectangle made up of 4 triangles carefully constructed as follows. So I've just colour-coded them from ease, the black, the red, the blue and the green one. What I then need to do is label the vertices like so. I'm going to start with D. I could have started at C to be fair. But D, E, F, G, H, I going anti-clockwise from the bottom left corner. Next, what we're going to do is just take these corners, these angles, and just make them slightly easier with some labelling. And we're going to define this length DH as 1 unit. Angle EDF here is going to be just called angle A. Angle FDH in the blue one here we're going to call angle B. DHI in the black triangle at the top we're going to call A plus B, and the red one, angle GFH here, is also going to be called angle A as well. So we just need to add these on like so with the labelling. So at this point, with all these different triangles and different angles, you might be thinking, is that really making a triangle? Do those fit together and make 90 degrees where they need to? Does this make 180 degrees and makes a straight line? Well, it can't hurt to just stop for a second and just convince ourselves this is definitely a rectangle and this proof is actually going to work. So let's start off with the green triangle at the bottom. So if we have a look at angle DEF, that's the 90 degrees and that's angle A. So if we also then just take a look as well at the green one, because angle E is a right angle, this one here is A, and because angles in a triangle add to 180, this one here in the top right, DFE, that's going to be 180 minus 90 minus A, which will just be 90 minus A. So let's label that one on, like so. Then if we have a look at the 3 angles meeting at F, we've got 90 minus A here, A there, so 90 minus A plus A gives us 90, and this is a right angle too, so 90 from these two plus another 90 is 180. And so this side here, from E to F to G, is indeed a straight line, because angles on a straight line add up to 180, which they do. So that fits, that works as it were, and so that side is a straight line. So in the same way, we can see exactly with the same reasoning that in the red triangle, angle H must also be 90 minus A. So we can have this on as well. Next, if we think about the 3 triangles made up at point H here, we can show that this needs to be a straight line too, because IHG needs to be a straight line because it's a rectangle. So, if we think about this here, that's A plus B, that's 90 minus A. If we add these two together, minus A plus A's cancel, so we're going to have 90 plus B. Angles in a triangle, of course, need to add up to 180. So I've got 90 plus B so far. I need an extra 90 to go here, and that plus B needs to cancel. So this one here needs to be 90 minus B. So again, we can add that one on. Next, if you look at the blue triangle in the middle, it also works, and the blue triangle's angles also add to 180 degrees now. 90 minus B plus B is 90, plus a right angle, that gives 180. So we're all good. Finally, for the entire outer shape to be a rectangle, we need angle IDH, this one here, we need to prove that's going to be 90 degrees as well. So let's think about this. So this here to be 90 degrees in total, this bit needs to be 90 minus B minus A, because the blue B plus the green A plus the 90 minus B minus A will then all add up to 90 degrees. So we can label this on here as being 90 minus A minus B, 90 minus A minus B, plus B plus A cancels to thus leave with 90 in total, which we need. You can also now see that the angles in the black triangle also work, and the angles in the black triangle now add up to 180 degrees as well. A plus B cancels with the minus A minus B, so we just have a 90 there plus 90 there, so that's 180. So that hopefully proves that it is indeed a rectangle like I'm saying. I'm not trying to fool you, it does work, so we're all good to go. So these angles have put in the dotted lines. We can get rid of these now for simplicity, so we can just focus on the actual main bit of the proof. So let's get started. So I did promise you SOHCAHTOA, some basic right-angled trig, so let's wheel out the good old SOHCAHTOA triangles and consider the blue middle triangle. So what we need now is to work out the opposite side, HF, this one here in the blue, in terms of angle B and the hypotenuse 1, we can use this SOH triangle here. So sine B is the opposite, which is HF over 1. So side HF is simply going to be sine B. Just times in both sides by 1 doesn't really do anything. HF is sine B. So let's label that one on. HF is now sine B. In pretty much exactly the same way, using the CA triangle, we can see that side DF down here must be cos B. Convince yourselves of that if you're not too sure, but it's not hopefully too hard. In pretty much an identical fashion, if we consider the black triangle that has the same hypotenuse as 1, as you can see there, then what we can do here is calculate the other lengths in terms of its sides, in terms of this angle A plus B. So in the same way, the opposite will be sine of A plus B combined, and this one here will be cos of A plus B combined as well. Next, let's look at this bottom green triangle as well. So we've got its hypotenuse labelled. Its hypotenuse here is cos B, and as well as that, in terms of cos B and angle A, we can define sides DE and sides EF. So using that, what we can do is we can say that sine of A is the opposite, FE over cos B, and that cosine of A will be the adjacent DE over cos B. So if we arrange both these, FE is going to be sine A times cosine B, and side DE is cosine A times cosine B. So again, we can just label those on our diagram as well. So now if we have a look at the red triangle, we need to do similar, and that's feeling a bit left out. So let's now, in pretty much the same way, get expressions for sides FG going up and HG going along. Again, we can use SOH and CA. So sine A is going to be the opposite, which is HG or GH over the hypotenuse, which we can see for this red triangle, sine B. And cos A is the adjacent, which is GF or FG, whichever way around, divided by the hypotenuse, which again, as I said, was sine B. If we arrange both these equations to get GH and GF, we see that GH at the top can be labelled sine A sine B, and GF down the side here can be labelled cosine A sine B. So let's label these on like I keep saying. So there we have. So the next thing now, the good news is you've pretty much done most of the legwork. So for a moment what we're going to do is just take a step back, forget the trigonometry for a second, and just focus on the opposite sides of this rectangle. Opposite sides of a rectangle are of course equal. So let's just think about the left side and the right side of this rectangle, which I'm highlighting in yellow here. So we can see that sine A plus B, which is the length of the left-hand side, that must be equal to the right-hand side, which is sine A cos B plus additionally cosine A sine B. And that gives us our first key result. So just equating the left and right sides, sine A plus B is sine A cos B plus cos A sine B. So as an equation, there we have it. So now if we just think about the top and bottom of the rectangle instead of the left and right, so those can go away, considering the top and bottom now, we can see that the top, which is cos A plus B plus sine A sine B, must be the same as the bottom, which is cos A cos B. So if we now just subtract sine A, sine B from both sides of that relation, we can isolate cos A plus B. So cos A plus B plus sine A sine B is that. So like I say, if we take away sine A sine B from both sides, what we'd get instead is cos of A plus B is cos A cos B minus sine A sine B. And that's our second key result as an equation. So I just need a bit more space here, so I'm just going to shunt this result up ever so slightly like so. So there we go. We mentioned GCSE, perhaps, and definitely year 12, you should hopefully remember that tan can be defined as sine over cos. So what we can do here is we can express tan of A plus B as sine of A plus B over cos of A plus B, like so. So our sine A plus B is this one here on the top, and cosine A plus B, this expression we put on the bottom. And of course that looks like an absolute mess. But we can simplify this by dividing both the top and the bottom of that fraction by cos A cos B, like so. Now of course that still does look like an absolute mess, but cancelling and simplifying, we can cancel cos B there. We can cancel cos A and cos A here. We can cancel cos A, and cos B there. So just putting in these cancellations like so, we can knit this up and eliminate an awful lot like this. Because all of that cancelled, that can just be called 1, because anything divided by itself is 1, and these ones here can be eliminated as well. So what we're going to have here is just on the top sine A cos A, sine B over cos B. And on the bottom, this is a bit different, but essentially, sine A over cos A is tan A, and sine B over cos B is tan B. So this is definition of tan of A, that's definition of tan B, and this here is definition of tan A, tan B. So replacing those with the appropriate tans and getting rid of the sines and coses, we end up with this here. So tan of A plus B is tan A plus tan B, all over 1 minus tan A tan B. I don't really like how this looks, it's quite gappy, so I'm going to get rid of this fraction here and just make it look a bit nicer by putting it a bit closer together and with these as well. So those are the three main ones, looks neater. How about the other ones where we've got sine A minus B, cos A minus B, and tan A minus B? Rather than making a horrible shape like this with lots of weird labelling, what I'm going to do here is just use some pre-established identities with a cast diagram from year 12. So you might need a bit of year 12 knowledge, but I'll try and catch up and explain as we go. So, moving forward. Proving formulae for sine A minus B, cos A minus B, and tan A minus B. So we've already got the following from before, these three identities, so I'm just going to wheel them back in like that. So what we're going to do here, we can substitute in place of a B, minus B instead. So if I just highlight that and add that one in, then sine A minus B, we can think of as sine A plus in brackets minus B, which is sine A cos of minus B plus cos A sine of minus B. And the others in very much the same way, if you want to read those yourselves, rather than me just boring you with the details. So just making a little substitution, essentially. So now we need to think about the cast diagram. So on the cast diagram, I'm going to label the sizes, the magnitudes of each of these angles in the cosine, all, sine, and tangent sections as having magnitude of B. But of course we should know using a cast diagram that going anti-clockwise is for positive angles and going clockwise is for negative angles. So if I just box this off, then in the all section, that's positive B, and down in the C section, going from this axis down here, that's angle minus B. So we can rederive from year 12 some identities that relate positive causes, negative causes, sines and negative sines, and so on. So in the C quadrant, only cosine is positive. So cosine of minus B will be the same as cosine of positive B. They'll both be positive. So cos minus B is one and the same as cosine B. So what we can do here, we can replace these cos minus B's with simply cos B's, and the signs won't change. So I can say goodbye to these and sub in just good old cos B. So that neatens it up. But then we need to think about the sine minus b's and these tan minus b's. So again, thinking about this C quadrant here, sine minus b down there is negative, but sine of positive b is positive. So we can say there that because, same deal for tangent as well, sine of minus b is minus sine b, and tan of angle minus b is minus tan b. The magnitudes of tan of both is the same, but one's positive in the A quadrant and the other's negative because it's in the C quadrant. So we can replace the sine minus b's with sine b's first of all, so say goodbye with those, and put sine b's in. However, because it's minus sine b, that plus will change to a minus, and that minus will be a minus minus, which becomes a plus. So we need to just put sine b's back in again, and then switch these signs over, like so. Do the same with the tans, so replace the tan minus b's with tan normal b's, so say goodbye to those, add in tan b. But in the same way as before, because it's actually the same as minus tan b, I need to switch this sign. So plus tan b will become minus tan b, and this minus here will switch to a plus. So just switching these signs over like so, we've got the results. Making it look a bit neater, getting rid of all this, we can see here they've got pairs. So the sine formulae, we've got these, the cosine formulae are these two here, and finally the tan compound angle formulae, we've got these here as well. So they're proven, so hopefully that makes more sense and is more convincing than just saying it in a lesson, hand waving and quickly moving on. So if you were curious, I hope that's helped to some extent. So that's all from me. I'll keep it as short and sweet as I can. Finally, just to say sincerely, thank you for watching that, and I hope it's been useful to some extent. Please do subscribe and watch other videos if you can do, that's always nice. Ask me in lessons if you're unsure about anything, and I do hope to see you all very soon. So from me and Mr. Bailey, it's goodbye once again.